In 1947, a newly independent India was contending with a 12% literacy rate, widespread poverty, and the massive socio-economic fallout as partition. To international observers, prioritizing a space program in this environment appeared to be a gross misallocation of scarce resources. Prime Minister Jawaharlal Nehru recognized a different reality. He argued that cultivating a national scientific temper was not an academic luxury, but the only practical method to accelerate India's developmental timeline and solve ground-level crises. This vision was operationalized by Dr. Homi J. Bhabha. Having already established India's atomic energy infrastructure, Bhabha leveraged his administrative wheat to formalize funding for upper atmospheric research. Dr. Vikram Sarabhai took the scientific reins, establishing a strict philosophical mandate. He determined that India would not compete in Cold War geopolitical space races. Every rocket and satellite had to directly serve the public, improving weather forecasting, telecommunications, and resource management. The space program was engineered as a mechanism for national survival. It was an investment in basic infrastructure, utilizing the vantage point of orbit to solve problems down on the Earth. The physical origin of this effort required specific geography. The magnetic equator, where the Earth's magnetic field is perfectly horizontal, runs directly over the southern Indian fishing village of Thumba, making it an internationally crucial site for studying the ionosphere. Local residents relocated to accommodate the scientists, offering up the St. Mary Magdalene Church. The altar was cleared to serve as the primary design office, and the bishop's house was converted into a mechanical workshop. The contrast between the hardware and the transport methods was stark. When preparing the American-made Nike Apache-sounding rocket for its 1963 launch, engineers transported the nose cone and payload instruments to the launch pad on a bicycle to avoid damaging sensitive equipment on unpaved roads. This early committee, INCOSPAR, underwent a structural evolution. By 1969, it matured into the Indian Space Research Organization, or ISRO. 3 years later, the government formed the Space Commission and the Department of Space. This institutional design was highly intentional. By placing the Department of Space directly under the portfolio of the Prime Minister, ISRO bypassed standard bureaucratic friction. Engineers could test, fail, and iterate without the drag of interdepartmental politics. By the 1970s, ISRO proved it could construct functional orbital hardware with satellites like Aryabhata and Bhaskara. However, getting them into orbit required purchasing payload space on Soviet and European rockets. Achieving full autonomy required building a domestic launch vehicle. The mandate to develop the PSLV-3 forced ISRO into the harsh reality of rocketry, where minor aerodynamic or structural miscalculations result in immediate, catastrophic losses. Under the leadership of Dr. A.P.J. Abdul Kalam, the first PSLV-3 flight in 1979 ended in a devastating crash into the Bay of Bengal. Analyzing the telemetry data, Kalam and his team corrected the propulsive faults and successfully placed the Rohini satellite into orbit a year later. Resource limitations constantly required unorthodox engineering tests. In 1981, scientists needed to test the telecommunications antenna on the Apple satellite in a completely non-magnetic environment to prevent signal interference. They solved this by placing the advanced orbital satellite on a wooden bullock cart, isolating it from the metal chassis of standard trucks. Upscaling the payload capacity led to the PSLV program, which suffered multiple mid-air structural failures. Engineers harvested the telemetry from these crashes, using the harsh flight data to heavily modify the staging systems for their next design. These overlapping crises of tight budgets and exploding hardware forged a distinct institutional culture. ISRO engineers learned to extract maximum data from catastrophic failures, engineering solutions that relied on mechanical ingenuity rather than massive financial backing. Lifting heavy communication satellites requires cryogenic propulsion. This involves handling liquid oxygen and liquid hydrogen at -253 degrees Celsius. If the turbopumps fail to mix these deeply frozen liquids at exactly the right pressure, the entire engine will instantly combust. In the early 1990s, India attempted to acquire this technology from Russia. Citing the Missile Technology Control Regime, the United States imposed sanctions and successfully blocked the transfer of the cryogenic engine designs. Locked out of the international supply chain, ISRO committed to building a cryogenic engine from scratch. It required nearly 2 decades of localized metallurgy and fluid dynamics testing to successfully hotfire the indigenous CE 7.5 engine. Simultaneously, the hard lessons from earlier launch failures culminated in the PSLV. This rocket utilized solid and liquid propulsion stages to become one of the most statistically reliable launch vehicles on the planet. The foreign technology embargo forced ISRO to develop internal supply chains and independent propulsion technologies. Denying India the hardware directly accelerated its transition into a fully self-reliant aerospace manufacturer. Mastering orbital mechanics allowed ISRO to look past Earth. In 2008, the Chandrayaan-1 lunar mission deployed an impact probe that conclusively detected water molecules on the lunar surface. 5 years later, the agency targeted Mars. The Mangalyaan mission had strict payload limits, meaning the spacecraft carried highly restricted fuel reserves and could not rely on raw engine power to cross the millions of miles of deep space. Instead of brute force, ISRO utilized complex mathematics. They executed a series of gravity assists, firing the engines at specific perigees to stretch the spacecraft's elliptical orbit. Once enough kinetic momentum was gathered, they essentially used Earth's gravity to slingshot the probe toward Mars. This chart highlights the financial reality of that mission. Mangalyaan cost $74 million. By relying on orbital math instead of heavy launch vehicles, ISRO executed a deep space mission for a fraction of the cost incurred by Western agencies. India became the first nation to successfully enter Martian orbit on its very first attempt, inserting a functioning scientific payload exactly where they intended. This frugality evolved into a major commercial advantage. Global private companies and foreign governments began purchasing space on ISRO rockets, recognizing that the agency could deliver commercial payloads into precise orbits at a significantly lower cost. Deep space exploration carries inherent risk. In 2019, a software glitch caused the Chandrayaan-2 lander to crash into the lunar surface during its final descent phase, leaving the mission team to rebuild and attempt the landing again. The target was the lunar South Pole. It is a region completely devoid of flat terrain, covered in deep shadows and massive craters that confuse autonomous navigation sensors during the final critical moments of a soft landing. In August 2023, the telemetry held steady. The Chandrayaan-3 lander fired its braking thrusters, navigated the cratered terrain, and successfully touched down, making India the first nation to land near the lunar South Pole. Millions of people watched the descent live. It served as a massive validation of the domestic engineering sector and solidified India's technical standing among the global space powers. ISRO is now manufacturing hardware for the Gaganyaan mission to place Indian astronauts into orbit, with a formal timeline set to construct and deploy a permanent, modular space station by 2035. Over 70 years, a program that started by testing rockets in a fishing village has mastered cryogenic propulsion and deep space telemetry. ISRO demonstrated that investing in scientific capacity is the most effective way for a nation to write its own future.